Project Ugnay, an SSVEP-based BCI speller and communicator for elderly and people with severe motor disabilities.
Project Ugnay is envisioned as a communicator for people with neuromuscular disabilities such as stroke and ALS, as well as elderly people with reduced mobility. The system is a brain-computer interface which uses brain signals to control a computer and coordinate functions. The concept of steady-state visually evoked potential, which is the brain's natural response to visual stimuli presented at a certain frequency, serves as the input to the BCI system. The system features a speller and basic needs communicator, which will enable the patient to type words, sentences, and selected urgent needs for the purpose of communicating with the people around him or her. The selections are presented in flickering boxes, each with the specific frequencies. The patient can communicate through the selection by simply looking at the flickering box of choice, which require very minimal physical movements. The purpose of the study is to design and develop a brain-computer interface with speller and basic needs communicator based on the concept of steady-state visually evoked potential using a low-cost EEG device. Furthermore, the study aims to achieve the following. First, to design a subsystem that will utilize open BCI ganglion in a SSVEP-based BCI speller and basic needs communicator. Second, to implement a Butterworth bandpass filter limited to 5 Hz to 30 Hz and to perform discrete Fourier transform for feature extraction on the raw EEG data. Third, to train the system using artificial neural network, K-nearest neighbor, and support vector machine learning techniques to classify the SSVEP signal as having a resonant frequency of 9 Hz, 11 Hz, 13 Hz, 15 Hz, and 17 Hz. Fourth, to create a graphical user interface that will evoke the corresponding visual stimuli and present a BCI speller which contains all the letters of the English alphabet, delete, spacebar, and toggle button, as well as the basic needs communicator which contain 5 basic needs, command, and toggle button, each of which having a unique frequency of flickering. Fifth, integrate an offline and online text-to-speech engine. Sixth, to develop an Android mobile application that will serve as an interface between the patient and another person. 7. To test and evaluate the accuracy of the designed SSVEP-based BCI speller and basic needs communicator. To address the problem of the lack of means for impaired individuals to communicate with the world around them, a BCI system which consists of a BCI speller and basic needs communicator was designed. To obtain and record SSVEP responses, a low-cost EEG sensing device called Open BCI Ganglion was used. 3 wet electrodes are attached on the OZ, O1, and O2 electrode location on the occipital region of the brain, along with 2 electrodes on the A1 and A2, point on 2 earlobes to serve as ground and reference. The occipital region was targeted since SSVEP responses are most pronounced on this region. Recorded signals will be passed through the main processor, the app board via Bluetooth. This device will also handle signal processing, which includes a Butterworth filter limited to 5 until 20 Hz, Fourier transform for feature selection, as well as machine learning. Upboard will also coordinate the delivery of visual stimuli and text-to-speech output on the LCD TV. It will also handle internet connectivity with the external Android application. The revised GUI for the speller and basic needs both features 6 flickering boxes with the following frequencies: 7, 9, 11, 13, 15, and 17 Hz. The speller features 2 levels of selection, which contains all the letters of the English alphabet grouped in 6, as well as to speak, space, delete, send, and separate toggle selection, which leads to the basic needs. The basic needs GUI feature 5 basic need commands and a toggle selection, which leads to the speller. A display panel is provided on the upper part for displaying typed words, and while a chat box panel for sent items is located on the right side.
Block diagram. The process begins by ensuring the proper attachment of the 3 wet EEG electrodes on the OZ, O1, and O2 regions of the scalp and the 2 ear clip electrodes. After following the prescribed boot up process, which includes turning the system on, activation of the data stream through the OpenBCI software, and the proper selection of the working mode of the system, the device is ready to use. Upon startup, the system will present the first GUI where the user can select between the speller or basic needs GUI. Based on the selection made, the system will load the corresponding GUI. The GUI is presented to the user through the LCD screen, which is also capable of handling the TTS audio output. This is connected to the upboard via HDMI. The OpenBCI ganglion is responsible for handling the recording and transmission of EEG data via Bluetooth dongle to the main processor, which is the upboard. The system will continuously present the visual stimuli through the GUI to the user just as the EEG device is streaming. A trigger button connected to another microcontroller is provided to indicate to the system when it should start recording the data stream, which is due to the response of the user to an intended selection, by looking at any of the blocks in the GUI which flickers at a certain frequency. Once pressed, the system will record the following 5-second stream of data. The data will then be subjected to a filter which is limited to 5 to 20 Hz. Fourier transform for feature extraction, the signals from the 3 electrodes will be averaged before being classified through the machine learning. Necessary selection from in the form of a letter, command, or basic needs statement will be reflected in the display panel on the screen once completed. For an online system, the Chatlight Android application is enabled via cloud and the online Google TTS is active. Conversation will be logged on the chat box on the right of the screen. Meanwhile, if the system is offline, the connectivity with the application is not possible while the onboard offline eSpeak is on standby for use.
Ideally, system can be divided into two subsystems, namely the EEG device subsystem and the processing subsystem. The former is composed mainly of the OpenBCI ganglion, 3 wet electrodes, 2 ear-clipped electrodes, LiPo battery, and headband, while the later is that of the upboard microcomputer, Arduino Nano, and push-button module, and the LED TV. OpenBCI ganglion is an open-source brain-computer interface hardware which is capable of recording and monitoring the electrical activity of the brain, muscle, heart rate, body movement, and other biosensing features. This board is compatible with standard EEG electrodes, but for the case of our project, gold cup wet electrodes are used. The ganglion board is the device which records the EEG signal in the form of SSVEP produced by the user's brain after being exposed to the flickering stimuli. Upboard serves as the main processing unit for the system. It is responsible for receiving and processing the raw data from the ganglion board, signal processing, signal classification through machine learning, and controls the display of the GUI and other outputs, including audio, on the LCD screen. This should also handle the connection between the system and the other application via cloud if online. For the case of our project, it used Windows OS. The ganglion dongle and Arduino Nano are connected to the board USB ports while the LCD display is connected via its HDMI port. For the case of OpenBCI ganglion, we designed it to be able to be attached in the arm of the user. The shape of the case was adopted in the OpenBCI ganglion. Presented on the next slides are the CAD layout for OpenBCI ganglion case and upboard case.
The general flow for the whole system started in checking if the OpenBCI ganglion battery is still charged by turning on the blue indicator light. If the light is on, connect the wet EEG electrodes to the board as channel 1 for O1, channel 2 for OZ, channel 3 for O2, 2 ear clips electrodes to the ground and reference. Otherwise, disconnect the battery from the OpenBCI ganglion and connect it to the battery charger. Apply conductive paste onto the 3 wet electrodes and attach it to the scalp along with the 2 ear clips. Then secure the EEG case under the user's arm. If the electrodes are properly attached, turn on the ganglion through the switch. Plug and boot up the upboard and other devices. Connect the Bluetooth dongle into the USB port and load the OpenBCI software. Make sure that the indicator for the reference and channels 1, 2, and 3 are in green. Click the Start Data Stream and make sure that the readings for channels 1, 2, and 3 are low, around 5 to 70 micro-VRMS. Then activate the main GUI. The assistant must select between an online or offline system by clicking the Settings button. Inform the user that the system is ready and allow the user to control the trigger as he or she wishes. If the trigger button is pressed, two blocks will start to flicker at their assigned frequency, and the computer will be given a go signal to start recording the incoming EEG signal which is due to the stimuli, subject to the recorded EEG response to filtering, fast Fourier transform, machine learning identifier. 7 Hz was identified as the resonant frequency. Proceed to the BCI speller system GUI. Otherwise, if 11 Hz was identified, proceed to the BCI basic needs communicator system GUI. The system presents an analysis and interpretation of the data and results obtained from the testing the device. The development process of the system, which includes data gathering, machine learning, hardware and software development, as well as the testing procedure conducted, is discussed in this depth on this chapter. The Project Ugnay system is composed of several subsystems, each performing a unique task which handles EEG signal acquisition, presentation of visual and audio outputs, data processing, and mobile communication. System development involves the implementation of the following. First is the implementation of the transmission and recording of EEG signals. The transmission and recording of the EEG signals, which is a result of exposure to the visual stimuli presented, is an essential part of this system. This serves as the primary input to the system. The acquisition of the important signal is the beginning of the function of the system. Next is the SSVEP-based BCI composed of implementation of the main GUI. The SSVEP-based BCI speller and BCI basic needs communicator are two different GUIs within the system. The system user has to make a selection of which part of the BCI he or she desires to use. The main GUI of the system is the first GUI which the user will encounter. It features two flickering boxes indicating communicator and the basic needs. Next is the implementation of the BCI speller. One of the two major features of the Project Ugnay SSVEP brain-computer interface is the speller. It is a GUI which enables the user to type words, to create phrases or sentences, to communicate with other people around him or her. Next is the implementation of the BCI basic needs communicator. Another major feature of the Project Ugnay SSVEP brain-computer interface is the basic needs communicator. This GUI features 5 basic needs commands which relay the need for food, water, sleep, and assistance presented with a corresponding graphic. The basic command, when selected, automatically keys in a phrase and communicates this immediately with the people around the user. For testing the implementation of the Open BCI ganglion, based on the results indicated in the table, it shows that the acquisition of the EEG signal was successful and that a successful connection between the ganglion board and app board has been achieved. Next is the testing the main page. The assessment shown on the table is marked as successful since in every selection of the command for trial 1 and 2 are correct. For the testing of the BCI speller, the assessment shown on table is marked as successful since in every selection for each of the two levels, the intended block or letter appeared correctly. For trial 1, the intended block for level 1 was A, B, C, D, E, F, and for level 2, letter A was intended. Both are successfully chosen correctly without any error, as well as for the trial 2. Lastly, testing the BCI basic needs communicator. The assessments shown on table for trial 1 and 2 are marked as successful since in every selection in the basic needs communicator, resulted a correct command.
After the system has been implemented with the integration of the hardware and software components, the following conclusion has been made. First, the researcher was able to utilize the open BCI ganglion in the development of an SSVEP-based BCI speller and basic needs communicator. Second, the project was able to perform the necessary signal processing for the EEG signals. Third, the researchers were able to train the 3 machine learning models using recorded SSVEP EEG signals. The training with the artificial neural network has resulted to the highest accuracy across the 4 GUIs. An accuracy of 100% was achieved for the main GUI, 98.33% for the first level of the speller, 98.89% for the second level of the speller, and 97.78% for the basic needs communicator. Fourth, the researchers were able to create a functional graphical user interface which were able to display the visual stimuli in the form of flickering green boxes to evoke SSVEPs. Fifth, the system was not able to perform a text-to-speech functions which would have allowed the system to convert the text type on the BCI system into audio for both offline and online mode through eSpeak TTS engine and Google TTS engine respectively. 6. The researchers were able to begin the development of the mobile application. However, the application has not been fully implemented and was not able to fulfill the required functions from it. Lastly, the BCI speller and BCI basic needs communicator of the system was successfully evaluated for their accuracy.
For the recommendation, first is, controlled environment is a better location in performing the SSVEP brain-computer interface system since any form of distraction can affect the behavior of the incoming signal from the EEG device and eventually the overall accuracy of the system. Second, future researchers can explore the SSVEP response produced by using other colors. Selecting a color which will evoke higher responses and further improve the comfort is highly encouraged. Third, the use of a monitor with a higher refresh rate must be explored. The refresh rate of the screen has been observed to limit the capability of the stimuli in evoking the proper frequency. Similarly, this will also require the use of more powerful graphic processor to handle the higher refresh rate. Higher frequencies can be tested given this setup. An improvement to the software which handles the flickering boxes must also be explored by future researchers. The fidelity of the flickering to the assigned frequency must be ensured so to evoke responses only on the desired frequency and not spreading out to nearby frequency as observed in the study. If signal fidelity cannot be ensured, it is best to keep enough spacing between the two frequencies like what was observed on this study. Fifth, the spacing between two frequencies can be reduced to be able to integrate more functions to the BCI. For the case of the study, which observed 2 Hz spacing, reducing it to only 1 has the potential to double the number of usable frequencies. Sixth, exploring other designs for EEG headbands as well as new technology on EEG electrodes could improve fidelity of signal recorded, improve user comfort, and consequently usability. Seventh, innovation on the design of the EEG device and its placement is suggested in order to reduce setup time and avoid causing of failed signal readings which affects signal classification and prolongs waiting time. A portable setup which brings together all the system functions will be significantly improvement as compared to the modular approach taken to the present study. The study has targeted 3 electrode locations on the occipital region of the scalp, namely OZ, O1, and O2. Future researchers can explore other locations within the region, although these locations have been found to provide very stable signals with high correlation to the visual stimuli on the study on SSVEP. Future researchers can explore innovative ways on how to avoid the use of trigger button to signal the start of the EEG recording. Responses from muscular response, which include eye movements and other body movements, can be integrated. This will produce system which integrates two biological electric response SSVEP, EEG response, and EMG responses into a single control system.
Welcome to the testing part. So first we are going to explore some of the subsystems of the project. What we have in front of us is the EEG device subsystem of the project, which includes the battery, a lithium polymer battery, our main EEG device, which is the OpenBCI ganglion, which is a 4-channel EEG device. Over here are our wet gold cup EEG electrodes, which will be attached to channels 1, 2, and 3, which are located here. And then these two will serve as the ground and reference in the form of ear clip EEG electrodes. And over here is our 3D printed case. This one is the upper part, which holds the battery along with the battery holder, which is screwed. And then on this part, this is the lower part of the case, which holds the OpenBCI ganglion in place. So shortly, we're going to attach these electrodes on its proper locations here on the OpenBCI, and we're going to enclose it. Another important inclusion to the system is our conductive base. So this will be applied in between the head and the wet EEG electrode. So we're going to this will be used to fill the space on the wet EEG electrodes. This one is our headband, which is a Velcro strip. This one is our EEG holders, which will secure the wet EEG electrodes, which already contains the conductive base. And then this one is our battery charger module. So this is how our EEG device subsystem looks like after it has been covered. As you can see, we have attached our 3 wet EEG electrodes on channels 1, 2, and 3 pins of our OpenBCI ganglion, and then we also have attached our 2 ear clip electrodes on the reference and digital ground pins respectively. As you can see, we have provided holes for us to insert screws to be able to secure the case, and then we have provided holes on 2 sides. This one is a hole for us to be able to access the on and off switch, and then this hole over here serves as an access for us to attach our EEG electrodes. On the lower part of our case, we have provided a means for us to attach a Velcro strap, so we can put it on our arms. But for the testing, we're just going to lay it this way for convenience. Before we could properly use the device, it is necessary for us to attach the electrodes on its proper location. On this video, we are going to show you just how it's going to be done. Our assistant grabs the conductive base, and now she will apply a thin layer of conductive paste on the 2 earlobes of the user. This will act as the ground and the reference electrodes. The 2 earlobes are identified as A1 and A2 EEG locations. As you can see, the assistant is clipping the ear clip electrodes to the user. Now, the assistant is reaching out for the first electrode, which is going to be attached on the OZ EEG location, which is on an area immediately above the inion, part of our head. So she's using her finger to locate the inion, and once she has located it, it's only immediately above the inion, where it should be attached, the OZ electrode. She has filled the wet electrodes with conductive paste prior to attachment. Now she's holding the second electrode, which is bound for the O1 region, which is only immediately to the left of the OZ EEG location. She again filled the wet EEG electrodes with conductive paste before attaching it to the scalp of the user. That is how it is going to be attached. Next, she grabs the third electrode and she fills it with conductive paste. It is bound for the O2 region of the scalp, which is only towards the right of the OZ region. Now, she gets hold of the headband where the EEG holder is attached. We have to secure the headband on the head of the user so the electrode will stay in place for the duration of its usage. It is important that the EEG holder is properly attached to the electrodes. And then by securing the Velcro strap, we are assured that the electrodes will be held in place. And there you have it. That is how you're going to mount the electrodes onto the user. But before we could begin, we must make sure that the user is at least 60 centimeters away from the screen. And that is verified by using a meter. And now we have completed the mounting of the electrodes. Before we could use the OpenBCI ganglion device for our system, we must make sure that it has been properly interfaced with our Windows system. To do this, we have to launch the OpenBCI application. First, we have to select the proper BLE device, which is our ganglion. After doing this, we can start the stream. To ensure that it has been properly attached to the head of our user, we should check the impedance. As you can see, a green indication suggests that we have attached the EEG properly. And now we can start the data stream. If you will observe, the data is railing and there's a lot of fluctuations. So we have to wait for the signals to relax. At the same time, we could turn on the data stream on the LSL side. We should continue monitoring the signal, and once it has relaxed, we can now start using the system. You can see that the settings button has been selected. We can see the online and offline selections there. The about button has been pressed. We can see the about GUI, then the authors. Then we are back to the main GUI, which contains a selection for the speller and the communicator. Now the user is going to make a selection. The user has selected the speller. The user has selected the block containing YZ, send, speak space, and delete. The user has selected letter Y. The user has selected the block containing A, B, C, D, E, F. The user has selected letter C. The user has selected the block containing YZ, send, speak space, and delete. The user has selected space. The user has selected the block containing MNO, PQR. The user has selected letter Q. A glitch has been observed, which is marked by a prompt. No selection can be made if there is a glitch observed. Yet another glitch has been observed. The user has selected the block containing YZ, send, speak space, and delete, and has successfully selected letter Z. Another glitch has been observed. The prompt again pops out. The user has selected the toggle button and moved on to the basic needs communicator. The user has selected I am in pain. A glitch has been observed. The prompt for glitch appeared. Another glitch in the flickering has been observed. The user has selected I am thirsty. The user has selected I am in pain. I need to go to the toilet has been selected. Another glitch in the flickering of boxes has been observed. The prompt again pops out. The prompt pops out indicating a glitch on the flickering of the boxes. I am thirsty has been selected. I am in pain has been selected. I am in pain has been selected once again. I need to go to the toilet has been selected again. Another glitch on the flickering of boxes has been observed, marked by a prompt. Another glitch has been observed. And that ends our trial for testing. One of the inclusions of Project Ugnay is an Android application which should serve as an interface between the assistant and the user in online mode. However, this has not been fully implemented. On the selection, we can see here the select device, an about button, which will lead us to a page which contains an information about what the project is all about. The help button, which will lead us to a window which contains a set of questions and answers about the project and how to use it. And that is an exploration of the Project Ugnay Android application. Thank you.